many of you are online. If you have a solution for low carbon energy to bring to the market, please talk to either Fernando or me, and we'll be very interested to work with you and to bring this solution to market. This webinar is actually our most successful event ever. So we have more than 1,000 registrations for the whole course. And this would not be possible without the involvement of quite a broad partnership. So here you see some of the organizations listed who helped us in pulling this course together. So we have University of Sevilla, of course, our main speaker for today. Global Solar Thermal Energy Council, the initiative promoting solar energy on a global scale. We have two associations, Estelia Solar and Protelmor Solar, specializing in concentration solar. Regal and CSP today are a media partner. So then, without much further ado, it is now my pleasure to introduce the main speaker. Manuel, the floor is yours.
Thank you very much, Hans. Thank you very much, Fernando, and good day to all of you. Well, it's a pleasure to be here with with people from so many places in the world. Today, in this first session or class about concentrated solar power, I'll start with some introduction, with some rather theoretical introduction to the benefits of solar thermal power, and then I will try to give a broad view on the on the CSP technology in general. The next days we will try to go some more in depth in the different technologies which are under the umbrella of CSP. Well, just to start with this, first I will try to define what are solar thermal concentrating systems. I like to define them as systems that make use of solar energy by first concentrating solar radiation and then converting it into thermal energy. There are three important terms there. First, we are talking about different uses. We are making use of solar energy by means of concentration, but these uses can be very different. It can be, for example, electricity generation, like in the case of solar thermal power, but there are other applications like industrial process heat, for example, for different types of industry and with different levels of temperature. Absorption cooling, which is a very nice application because the source is very well adapted to the use. I mean, normally when we have more sun is when we have a higher temperature, so cooling is an application very well adapted to the resource. Concentrated solar energy can also be used for chemical processes, like very different kind of chemical processes, like for example, hydrogen generation or production from for example, methane reforming, or other chemical processes of interest that require high temperature or heat. And well, we could talk about other applications like detoxification and perhaps a few more, but today we will concentrate mainly on electricity generation, on what is known as solar thermal power. The second interesting term is concentrating. Why concentrating? We will see that if we wish to take advantage of the excellent characteristics of the solar radiation as an energy source, we must concentrate it. And the third term is converting it to thermal energy because We are not talking about other technologies like, well, the most important one, photovoltaics, that convert directly solar radiation to electricity, but there is an intermediate step, the conversion from solar radiation to thermal energy, that, well, it has some interesting features. Well, after this, I'll talk about a little bit about the resource, the solar energy. Probably most of you know about it, but I think I should mention it. The solar energy is an abundant resource. It's it's available everywhere on our planet, on the Earth, at different levels, of course, and it's a high quality energy, as we will see immediately. We will later see what I mean with high quality energy. But despite of that, there are some problems, some difficulties for the use of solar energy as an energy resource for for different applications. The first such characteristic is that it's variable in time. That makes it difficult to use it. Makes it difficult to use it in some applications, like electricity generation, for example. It's not evenly distributed on space. There are regions, areas with large solar resource, and other regions with with a lower solar resource, and it has low density, what makes it difficult to use it again. So, if we take into account these characteristics, we will see, for example, from the point of view of the geography, this picture that you have probably seen many times before, shows the regions of the world that have better solar resource. From the point of view of CSP, we can see that among these regions we find the deserts on the southwest of United States and north of Mexico, deserts on north of Africa, Arabia, southwest Asia, and in the southern hemisphere in Chile, deserts of Atacama in Chile, South Africa and Australia. Large regions, most of them placed in what is known as the solar belt. These are the regions with a better solar resource from the point of view of CSP, of concentrated solar power. There are other regions that perhaps could have that have also acceptable solar resource. These regions are much larger. It's a large part of United States again, and southern countries of Europe, most of Africa, large regions in Asia, India, for example, South America, etc. These regions have something in common. They have many clear days, many days with a clear sky, which is very important for CSP. Regarding the quantity of solar energy, it's huge. In fact, there are studies, like for example the Desertec project. I know that there are some people, I've seen that there are some people related with this project in the audience, that show that 90% of the total electricity demand could be supplied from solar thermal power plants covering an area of 300 by 300 kilometers, square kilometers. The Desertec project, as probably you know, consists of installing large solar thermal power plants in the Maghreb area to supply electricity to Europe and Africa mainly through high voltage direct current connections. Well, we are talking about concentrated solar power as a general term, or concentrating solar thermal power. And the first, perhaps the first thing is that we could ask ourselves, why should we go to high temperature? And to answer to this question, I have represented here an ideal system that converts solar radiation into electricity or into work, into mechanical work, by first converting it to thermal energy. That is solar thermal power system, in fact. And we all know that if we wish to convert thermal energy into mechanical work or electricity, we can use a thermal engine, which takes heat from a source at high temperature, delivers work, and has to reject some heat to sink at lower temperature. This sink is normally the environment, in a general sense. The efficiency of these thermal engines depend on the difference on the temperature difference between the high temperature source and the sink. Normally, as I said, the sink is the environment, so the temperature is we cannot play much with that. That temperature is more or less fixed within our context, and therefore, if we wish to achieve high efficiencies, we would like to have high temperatures at the source. This is the reason for the high temperatures. Something very very simple. This system works by converting the solar radiation. By converting the solar radiation, I don't know if you can follow the pointer. Perhaps now, yes. By converting the solar radiation into thermal energy in an element, which is this one, which is called the receiver. Normally, this receiver works in the following way. We have a fluid that enters the receiver at low temperature and is heated in the receiver to low temperature, or increases its energy. It can be, for example, also an evaporation and state change. This fluid at high temperature is the heat source for the thermal energy. Okay. Well, we are talking about high temperature, but what does it mean? Well, high temperature means temperatures in the range of 1,000 degrees, and how is it that we can achieve these high temperatures with solar energy? Well, the reason is that the sun, as a heat source, is a heat source of very high quality, of a high equivalent temperature. What we can see in this diagram is in this blue line. We can see the extraterrestrial solar spectrum. That is the distribution of the radiant energy coming from the sun. If we make a simple approach, we try to imagine an ideal body, which is a black body that has the same temperature as the sun, that emits the same energy as the sun. We will find that the equivalent temperature of this black body, which is 5,777 Kelvin. That's 5,500 degrees Celsius. This is the energy emitted by such black body is represented with a red line, and we can see that it's very similar to the blue line. So in principle, if we were able to set solar thermal power system on top of the atmosphere before the sun interacts with the atmosphere, we would be able, theoretically, to achieve temperatures in the range of 5,000 Kelvin. Of course, the sun interacts with the atmosphere and loses some of the solar radiation loses some of the energy. We can see, for example, here the spectrum of the global irradiance for given conditions, which I won't go into details now, and the spectrum of the beam component, and of the diffuse component. Of course, if we calculated the equivalent temperatures of these components, it would be not as high as 5,000 Kelvin, but it would be still in the range of 2,000 or 3,000 Kelvin. Depends on the day and on the conditions. Okay. So we are able to achieve very high temperatures from the solar radiation. But then why we need to concentrate the solar radiation? We need to concentrate the solar radiation because it's clear that we wish to operate at the highest operating temperature we can achieve. But if we look at the receiver, we need some heat transfer mechanism here, and if we wish to achieve a given temperature in the fluid, the surface of the receiver must be at a higher temperature. If we take into account the laws of radiation, if the surface is at high temperature, it emits a lot of radiation, so we have a lot of losses. The thermal engine may be efficient, but the receiver is not efficient. So the system as a whole is not efficient. What can we do to avoid this this fact? Well, what we can do is to reduce the area, the surface of the receiver. The receiver is the element that converts solar radiation into thermal energy. These losses, these radiant losses, are proportional to the surface of the receiver and to the fourth power of the surface temperature, roughly speaking. So, if we wish to have high temperatures, we need to reduce as much as possible the area of the receiver. And then we come to the scheme of what could be an ideal concentrating system. This ideal concentrating system is made of a concentrator that concentrates the beam irradiance. Concentrate the beam irradiance coming from the sun. The beam component, the direct component of the solar radiation, is the only that can be concentrated. It's the component that has a directional character, and therefore it's the only that we can concentrate with conventional means. So we concentrate the beam component. In this process of concentration, of course, we have some losses, and then we convert in the receiver the concentrated solar radiation into heat, into thermal energy. Okay? The receiver is the element, is a very characteristic element of these type of systems, of CSP systems. The receiver converts solar radiation into thermal energy. At the receiver, we have different types of losses. We have losses, radiation losses. We have convection losses, conduction losses, different types of losses. But in the end, we get heat. Thermal energy at high temperature. Thermal energy at high temperature that we can use in a more or less conventional thermal engine to generate work or electricity, at the cost, of course, of rejecting part of the heat, because as probably most of you know, we are limited by the second law of thermodynamics that that states that it's not possible to convert completely heat into work by means of a thermal engine. So, so we can analyze this simple system, this ideal system, and of course the first thing we would like, according to what I have said before, is to have a receiver surface or an absorber area. That's probably a more appropriate term. An absorber area as small as possible. And on the other hand, we wish to make use of as much solar energy as possible. So the concentrator is basically a device that has a large aperture and small exit. The relation between these two areas is called the geometrical concentration ratio, and we would like to make it as big as possible in order to make the system efficient. But well, how far can we do that? In principle, if we look at the receiver has the best efficiency at the temperature of the environment, more or less, and the efficiency decreases with temperature. It doesn't decrease the same way at all concentrations. For small concentrations, decreases very rapidly, as we can see. I don't know if you see the pointer, but you can see in this in the curves on the left. And the larger the concentration ratio, the slower is the decrease in efficiency with temperature. In the limit, for very high concentrations, the efficiency would be almost constant for very high values of the concentration ratio. On the other hand, we had the efficiency of the thermal engine. The efficiency of the thermal engine is a function of this ideal thermal energy. The thermal engine is a function of the temperatures of the hot reservoir and the cold reservoir. And for example, we have represented here the efficiency of a Carnot engine, which is the engine with the highest efficiency from the point of view of thermodynamics. Well, if we combine these two, I will pass rapidly over this. If we combine these two, we get this family of curves for different values of the concentration ratio. We see that for low values of the concentration ratio, we get rather low efficiency, but we get the highest efficiency at a given temperature. This is the optimum temperature for this concentration ratio. The higher the concentration ratio, the higher the temperature, the optimum temperature, and the efficiency corresponding to this concentration ratio. So it's clear that the best would be to have a very high concentration ratio. We would get very high efficiency. In the limit, our system, we would get the efficiency of the Carnot engine, the Carnot efficiency. Okay. Well, so why, in fact, the concentration region, as defined before, is just a function of the areas, of the aperture area and of the exit area. But we cannot concentrate as much as we wish. There are some limits to the concentrations. There's a first physical limit to the concentration of solar radiation that comes from the fact that the sun is not a point light source. If we look at the sun, we don't see a point, we see a disk. And this disk has an apparent diameter of 32, it's a solid angle of 32 minutes of arc. So if we observe the sun, some of the sun rays come from the center of the sun, but there are sun rays that come from the edge of the sun. The rays are not perfectly parallel them when seen from a point, for example, in the concentrator. We know that by the laws of optics, all the rays which are parallel to the optical axis of the concentrator will be, if this concentrator is, for example, a parabola, will be concentrated on the focus. But because the rays are not perfectly parallel, the rays will not be concentrated all on the focus, but on a region in the surrounding of the focus. This region can be smaller or larger depending on the characteristics of the concentrator. The fact is that there is a limit to the concentration ratio, which is given by this expression that you can see here. In fact, if we, well, these terms, these refractive indices of the media can be cancelled, and we would get 1 divided by the square sin of this solid angle that subtends the sun. So there's a physical limit for the concentration of solar radiation. There are also other practical limits that comes from the fact that the concentrator surfaces are not ideal. They have some waviness, some irregularities that make impossible to, or well, that make, as a result, we don't concentrate as much as we can. With an ideal concentrator, for example, we would get, like we can see here, what we call an image of the sun, a very good image of the sun, almost almost a circle. But with an ideal concentrator, we don't get such a good image, but a deformated image, like we can see, for example, in the lower picture, with a wavy surface. Okay, so this is another fact that limits the concentration of solar radiation. There are some other reasons. For example, I will only mention it. I won't go into the details. But other factors, like for example, the fact that not all the beam radiation comes from the disk, from the sun disk, but some of the radiation comes from the edge. It's what we call the circumsolar radiation that comes from the surroundings of the sun, and sometimes is measured by the devices used to measure beam radiation. Of course, if there's a lot of circumsolar radiation, like we can see, for example, in the red line, this is the yellow line is the sun shape, what we call the sun shape for a clear day, and the red line is the sun shape for example, a hazy day. We can see that well, the apparent size of the disk would be larger, so we would not be able to get very high concentration ratios. Summarizing, it's impossible to, we have limits to the concentration of solar radiation, and these limits are given for the systems that concentrate on a line, on a focal line, like the parabolic troughs, the well-known parabolic troughs, or the compact linear Fresnel reflectors that probably all of you have heard of too. This limit is given by 1 divided by the sinus of the solid angle, and for the point focus systems like the power towers, or the parabolic dishes, this theoretical limit is the limit we saw before, is 1 divided by the square of the sinus of this solid angle. These limits give for the for the size of the sun the values of more than 46,000, a factor of more than 46,000 for the three-dimensional concentrating systems or point focus systems, and a little bit more, 215 or 220 for the system that concentrate on a line, for the two-dimensional concentrating system. Sorry. Well, for real systems, of course, we don't achieve these high concentration ratios. For example, for parabolic troughs, we get concentration ratios in the range of 80 at the moment. For towers, we get different concentration ratios, from some hundreds to a few thousands, probably. For parabolic dishes, we go always in the range of thousands, from 1,500 to probably 5,000 or 6,000 times. And with systems that are known as solar furnaces, we can go even to higher concentration ratios. These are the concentrations we can get with the real concentrating systems we are using at the moment. We could also use secondary concentration to achieve higher concentration ratios, but well, we will talk about that in another session. Well, so this is perhaps the theoretical basis of this technology of solar thermal power. And now I will focus on the electricity generation, and I will give just a brief overview of solar thermal power, of the past and present of solar thermal power. As I said before, in next sessions we will go in more detail into the different technologies. Well, first of all, why is solar thermal power so attractive? Why it's becoming so popular in some sense at the moment? Solar thermal power is 100% a renewable electricity source. That's the first thing to be said. And the second thing, perhaps less known or not so well understood, is that solar thermal power is based on very well-known technologies in general. All the materials used in solar thermal power plants are engineering materials, typical engineering materials: steel, mirrors, water, thermal oils, molten salts. Steel is widely used in the industry, as well as mirrors for different applications, from the mirrors of the cars to the mirrors we find in our homes. I don't have to say anything about water. Thermal oils are used in the petrochemical industry, so heat exchangers that use thermal oil are well known. The same can be said, perhaps to less extent, of molten salts, etc. We also need control technologies to control all our systems, but it's all something that it's very well known. From the point of view of engineering, we have turbines, we have heat exchangers, we have substations. All the elements are typical in engineering, in electrical engineering, mechanical engineering, thermal, control engineering, electronics engineering. It's a multidisciplinary field, but most of the components are well known. It's the integration that poses perhaps a challenge to the engineers, because all the components have to be integrated for an application which is not typical. It's not typical in the sense that, for example, most of the engineers are used to very stable and predictable energy source. For example, a fuel, gas, natural gas, or oil, or whatever, even a nuclear plant. We know we can control the source. In this case, we don't control the source. The sun is there, the clouds sometimes come, sometimes go, and that makes it difficult sometimes to control the system and to make it efficient. So it's the integration of all these components which is a challenge. And then another attractive feature of solar thermal power is that since we are converting solar radiation first into thermal energy, we can store this thermal energy and use it at any other moment. That is the thermal storage. We will talk about thermal storage in the fourth session. And of course, this gives a lot of possibilities. It gives the possibility of improving the control of the plant during transients, but also gives the possibility of shifting the electricity generation from part of the day to another part of the day where it can be more profitable or it's more needed. It's better adapted to the demand, for example. Hybridization. Storage and hybridization are closely related. Again, we have solar thermal power systems have two well-defined blocks. One is the solar field, the other is the rather conventional power block. And we can use this power block, which is there, with the thermal energy coming from any other fuel. It can be fossil fuel, like for example natural gas, but it can be also renewable fuel like biomass, those coming from biomass. The combination of thermal storage and hybridization make these systems really dispatchable in the sense of this word, which is used in the electricity industry. So solar thermal power systems are very well suited for centralized and distributed generation. Therefore, I would say that these technologies, in general, solar thermal power, has a very high potential of contribution to the electricity system during the next decades, during the future. I won't go into it, but the energy system in general is changing. It's perhaps going more distributed, more renewable, and I'm sure that solar thermal power has a very important role there in this energy system of the future. Well, solar thermal power plants are the electricity generating systems that use this concentrated solar power, and what you can see here is drawing of a general configuration of a solar thermal power plant. We will find always the concentrator. different types of concentrator, as we will see in 1 minute, different types of concentrators, but there will be always a concentrator that concentrates the beam component of the solar radiation. And this concentrated solar radiation is converted into thermal energy at the receiver. The receiver is the element where concentrated irradiance is converted into thermal power. Thermal power at high temperature normally, at least with a high energy. This thermal energy can be delivered to a power block, to, for example, steam turbine, and generate mechanical work. That's the basic solar thermal power plant. But this basic solar thermal power plant can be complemented with a thermal storage, where we can store part of the energy generated at the receiver, or all the energy generated at the receiver, and use it at any other time. Okay, and we could also have auxiliary boiler that makes use of a fossil fuel or biomass or any other fuel to generate electricity, to generate thermal energy and then electricity when the sun is not present and we don't have thermal energy stored. Okay, this is the basic configuration of any solar thermal power plant. All the different technologies that we will see during these sessions follow this this scheme. Now, what are the main concentrating technologies? Well, first thing I would say that perhaps classical thing is to classify the different technology variants of solar thermal power plants according to the concentrator. And if we go from lower concentration to higher concentrations, the first type of concentrator we find is the linear Fresnel reflectors. These are Fresnel concentrators that are very simple, probably very very economic too. But on the other hand, they are not able to achieve very high concentration ratios, and therefore they operate at rather low temperatures. Then we have the parabolic troughs. The parabolic troughs, like the linear Fresnel reflectors, are line focus concentrating technologies. In this case, we have a continuous surface concentrator, which is the parabolic trough. It's like a cylinder of parabolic section that concentrates solar radiation on the receiver, which is placed in the focal line. With this type of systems, we are achieving concentrations in the range of 80. We can probably achieve higher concentrations, but not much higher. And temperatures at the moment in the range of the 400. Probably in the near future we will be able to achieve some higher temperatures in the range of the 500s, perhaps. Then we have the power towers or central receiver systems, which where the concentrator is a field of individual mirrors or elements which are called heliostats. The heliostats concentrate and reflect the solar radiation on the receiver, which is placed normally on top of tower. These systems are point focus systems, are of the Fresnel type, and with large heliostat fields, we can achieve very high concentration ratios in the order of 2,000 or 3,000, perhaps, efficiently. And finally, with these more or less classic technologies. We have the parabolic dishes, which are parabolic concentrators, continuous surface parabolic concentrators, at least conceptually, and that concentrate all the beam radiation on the receiver, which is placed on the focus of the parabolic concentrator. With these types of systems, we can achieve very high concentrations. And I think perhaps I'm going slower than I thought, but I will take just 2 or 3 minutes more to give an overview of solar thermal power plants, of the present and past and present solar thermal power plants. Solar thermal power plants are solar thermal concentrating systems for electricity generation, and we can see here 4 examples, one of each technology, of the technologies that I have mentioned before, and a 5th picture of the SEX plants, which are an important reference for for solar thermal power plants. Concentrating solar power is not new. From the ancient times, from Greece, we have some stories about the use of the concentrated solar radiation. The most famous one is the legend of Archimedes, using mirrors as a war arm against the enemy army at Syracuse. More recently in the history, Leonardo da Vinci made some experiments, and there were other inventions during the Middle Ages. In the 17th and 18th centuries, the burning mirrors became rather popular. We can see here a picture of a burning mirror. But it's in the modern times when concentrated solar power becomes into the focus. By the end of the 19th century and beginning of the 20th century, we find a lot of inventions that make use of concentration of the concentration of solar radiation to deliver mechanical work, or like for example this engine made by Ericsson, this one that you can see here, I hope, yes, and other inventions that were presented at the Universal Exposition in Paris, or that became so interesting for the general public that deserved important spaces in popular magazines, popular science magazines like this one you can see here. Perhaps the better known experience is that of Schumann, an American engineer, who founded a solar energy company and installed a solar plant in Egypt. This is a picture of that solar plant, and well, as you can see, it's not very different from present parabolic troughs power plants. And well, those our inventions were favored by the fact that there was a concern about the use of the fuels, of the carbon and later oil. But it's in the 80s of the last century, when the solar thermal power plants become very well, again the focus of interest because of the oil crisis of the 70s, and there are demonstration power plants more or less everywhere in the world. In France, this one is the Themis plant in the French Pyrenees. In Sicily, this is the Aurelius plant in Sicily. In United States, this is the Solar One plant. Again, France, this is the solar furnace, which is a little bit older. And in Spain too, yeah, where we have where we had two different projects. The project of the International Energy Agency, which is this one that I'm trying to mark now, and this other, which is the project of the Spanish Ministry of Industry. These two projects joined in the 80s and became what is now known as the Plataforma Solar de Almería. More recently, well, after a few years of a lot of interest, those projects more or less were successful in different degrees, but the oil price became again low and rather stable, and there was no interest to continue with the development of solar thermal power, and there was only a commercial plant which was built in those years. It was they were the plants that the company Luz installed at the Mojave Desert in California, in the United States. A total of 9 plants with 354 megawatts of rated power in total. These plants were built between 1986 and 1991, and for a long time were the only operating solar power plants in the world. In 1991, the Luz company became into bankruptcy, and well, I have taken here the news from the New York Times, and you can see the comments of the chairman of Luz, Newton Becker. Our infant industry, solar thermal electric, has died. In fact, it was like that, or it looked to be like that for a few years, because there was no new project that became a reality during many years. There were different projects. These are some images of the Sol Gas project and the Colon Solar projects that were projects where our group participated in collaboration with other companies and research centers like CIEMAT, DLR, and companies like Sevillana and Spanish Utility and so on. But these projects never became a reality for one reason or another. And it was not until 2000, until this century, and year 2006 or 2007, when there are new projects. The first one is probably the Nevada Solar One project in Boulder City, near Las Vegas. It's a 64 megawatt plant of parabolic troughs. Then became the PS10, PS20, two power tower plants near Seville, near where I am now, in Spain. These plants were the first that came into operation thanks to the good incentives that the Spanish law of for the electricity system, for the electricity system in general, what is called the special regime, gives to these types of plants. And well, we can see here some images of these PS10, PS20 plants. And since that, we have seen many plants being built all over the world, more or less, especially in Spain, but also in the United States. For example, this Fresnel plant in Bakersfield in California, built by the company Ausre, this other Fresnel type plant in Calasparra in Spain, the Andasol plants near Granada, also in Spain, which are very interesting because they have been the first solar thermal power plants with a large storage system. They have a thermal storage system with capacity for 7 hours and a half at nominal conditions of the turbine. These plants are 50 megawatt each. Or the Puerto Llano one project in Ciudad Real, in the center of Spain, more or less, developed by the company Iberdrola, which has no storage. And we have been, during the last year also, we have seen some new projects with new technology, like this Sierra Sun Tower in California, which started to operate in summer 2009. It's a very special power tower concept. Or this recently inaugurated parabolic
Very
dish
well,
plant
thank you very much, Manuel,
in
for this
Arizona,
very
Maricopa Solar
interesting
Power
presentation.
Plant. We will talk
So,
about all these technologies in the
your
next
questions are welcome.
sessions.
I guess that there are
And
already
well,
many of
these
them.
were
So,
just some
as
examples.
it's now
Many more
6 in the
are
afternoon
being
here
built,
in
and
Europe,
I'm sure that during
we have
next years we
spent
will
1
see many
hour.
more, not only in
So
Spain
we
but also
will
in the United
go
States and
across
in other
some of them.
countries.
For sure, we will not have the opportunity to
Well,
go
at the
across all of
moment,
them.
nothing else. Thank you very
In the
much
meanwhile,
for your
I put
attention,
these
for being there. And
notes, so the
well,
recording and the
if you have any
slides
question,
will be available at the links shown in the notes pod. So relative to your previous questions, and now